Okay, so last time we finished talking about glucose. We talked about how we break glucose down through glycolysis. We run those glycolysis products, being things like pyruvate, turn into acetyl coenzyme A, and running that through the Krebs cycle. And then we talked about the ways that we use NADH and FADH, those high-powered versions of these kind of weird, funky batteries, to power things like oxidative phosphorylation through the electron transport chain. So now, what we're going to talk about is we've already talked and introduced this idea of moving back and forth between high sugar versions, highly compact versions of sugar, being stuff like glycogen, and moving down in complexity and freeing up energy along the way. We can go through things like glucose, and then we can do even further down in complexity and break it further down into stuff like pyruvate. We have talked about this in the past, and this is what we kind of finish things in on Monday. So if we take it a step further, right, we care about glycogen because glycogen is our long-term storage reserves. And we say long-term, we're really talking like medium-term. If we want to go very long-term, that's mostly fat. Fat is our longest-term storage system, right? I'm going to increase my glycogen stores initially, but then if I keep being in this highly fed state, I'm going to start packing things away in adipose. That's fat tissue. So this is kind of like the initial bit of savings that we kind of start dipping into when we enter into a energy expenditure. So we'll dip into glycogen stores, and then if we keep going further and further into energy stores, we keep running or keep using energy or whatever we're doing, then we'll start dipping into our long-term stores. So it's kind of a medium term, kind of how much we spend and reduce and use this energy, right? Plants do this as well, right? And this is why we are able to eat a potato and get a bunch of starch out of it. This is why we're able to eat corn and get a bunch of product out of it, because plants have already done this, mostly through the act of things like sunshine shining down, causing things like, my board's a little bit weird, right? Sunshine powering this system. Sun is putting energy in and allowing us to do things like take basic glucose and store it away for later. Well, when we are talking about what's happening inside of a person's body, this is mostly being regulated by ATP concentrations and by hormones. Predominant things like insulin and glucagon, right? If I want to do something like glycogenesis, right? If I want to take a precursor product and turn it into a higher complexity product, glycogen, I'm going to stimulate things like my liver to do this storage for me. The liver has a bunch of blood flowing through it, has a bunch of metabolic activity, so this is why it makes sense for the liver to be the ones responsible for doing this sort of thing. And the liver is only going to do this in high ATP concentrations, right? What does this mean? Essentially, the liver is well fed. The liver has plenty of energy. We're not taxing the liver. We're not hurting the liver at all. And the insulin that's being produced by the pancreas is saying broadly over the whole body, we have more than enough glucose that we would not need this glucose that we're trying to squirrel away as glycogen. Hey, let's store some of this extra stuff for a later day, right? For a rainy season, right? When it starts to tip in the other direction, that's when we'll start to release stored glycogen and then bring it back out as glucose, mostly being things like ATP depletion, as well as things like glucagon. Glucagon being the predominant hormone that is in our kind of fasting state. Hey, it's been a little bit since you've eaten. I actually kind of I had a really late dinner, right? So what I'm probably doing is I'm mostly starting to tip into this process. If it's been half a day, well then yeah, I'm doing this a ton, and right? How much we are dipping into this mostly has to do with how much glucose stores we have left. If you were to go out and use up a bunch of energy, go run around the block or whatever, then we're going to drop our glucose levels really, really quickly. So then we're going to make glycogenolysis happen faster. Right? We're vacillating constantly between things like hyper and hypoglycemia. Hyper means a lot of, hypo means a little bit of, or a small amount. Gly, meaning sugar, emia in the blood. Right? You're either hyperglycemic or hypoglycemic. We're moving back and forth between these pretty much all day. Gluconeogenesis being this thing that we had introduced this concept of, and we're now going to expand it way bigger, where we're going to take non-carbohydrate sources, right, and then turn them into glucose, right? So something that is a carbohydrate are going to be things like starches and sugars, right? Those don't count anymore, right? Those are already carbohydrates. So I have to be taking in things like fats. I have to be taking in things like lipid products and protein products and turning those into things like those carbohydrates. The big ones being things like glycerol and amino acids, and we'll talk way more about how we use glycerol here in actually just a second, and we'll talk more about amino acids when we talk about protein digestion. So that's glucose, right? But where did these lipids come from when we were trying to turn them into glucose in gluconeogenesis? Well, we break down things like lipids predominantly. This is the way we want to have gluconeogenesis take place, right? Remembering, we eat some fat, we breathe some oil, those lipids go into our body, we absorb those chylomicrons into our lacteals, and they get dumped into the bloodstream, eventually making their way to the liver. Now, the liver processes these lipids and makes them available. What do we mean when we say process them? Right? It's mostly managing concentrations of the major lipid components. One of the big ones is a triglyceride. Triglycerides are three things, right? These three fatty acids essentially stapled onto a glycerol backbone, right? So each of these fatty chains comes off and it's a triglyceride, right? The tri being these three fatty acids. This is what most of what we are talking about in storage. This is also happens to be most of what we are intaking when we eat like an animal's storage. So if I eat like milk fats, or if I eat cheese fats, or if I eat fat that's in like beef, right? That's mostly going to be in the form of triglycerides. They're operating in much the same way that humans are, right? We care about this when we talked about how we use these lipids for, right? Just to make sure that we're not only thinking of lipids in terms of energy. We also use these in lots of different things, communication methods, right? Cholesterol helps produce bile salts, and then bile salts help break down fats. So this is kind of a circle system, right, where bile salts help break down fats like cholesterol, but then cholesterol is also an important component of making bile salts. So you can see when this starts to fail, right, if you were to have like a zero cholesterol diet, then that starts to impact things pretty substantially, right? This is a big problem. It's one of the reasons why zero cholesterol diets are actually quite dangerous. Oops, my keyboard's not working now. Right, same way that we move between high storage and low complexity and high complexity in glucose, we move towards high complexity and low complexity, right? An individual fatty acid is not as complicated as having three fatty acids all together at once, right? So if I do lipogenesis, I make fat, and then I take a low complexity couple chains of fatty acids and a glycerol and staple them together. If I do things like lipolysis, I go the opposite direction, right? I break that lipo, I break that fat, and turn it back into the components that we use to build the fat in the first place. Triglycerides are the one that's most important. There are other fats that are out there, but mostly when we're talking about this in this class, we're going to be restricting ourselves to mostly just triglycerides, right? Lipogenesis is going to take place, again, anytime that we are well fed. We have plenty of energy. Our livers are certainly not ATP starved in any way, shape, or form. We have a bunch of glycogen stores. So, hey, if this was something where we needed glycogen, we could always turn these fats into glycogen. But if glycogen stores are also quite high, well, maybe I could store them in a more long-term method, things like fat, right? This is lipogenesis. Most of these, in most individuals, these adipose cells, these fat tissues, are going to show up at about a 50-50 ratio between subcutaneous and deep fat. Surface fat and deep fat are two very different things. Surface fat, the subcutaneous fat, skin fat, you can sometimes hear it be called, is not that bad of a thing, right? It's mostly One of the reasons why kids have like a characteristic kid appearance in their face is they generally have a fair amount of subcutaneous fat. They actually tip a little bit more towards subcutaneous. One of the big problems with morbid obesity tends to be in the deep fat pockets. The effect of fat developing around tissue, particularly like visceral fat showing around your organs, that's when we start to see a bunch of red flags that will start to pop up. Mostly things like heart attack, liver disease, kidney disease, putting pressure on the spleen, putting pressure on the liver, right? That's mostly coming from that deep fat. That's mostly what we care about. So let's do a little thing on lipolysis. And so let's draw like the first half of lipolysis here. I think this is gonna work. Hey, yeah, it worked. Okay, so if we are talking about lipolysis, we are familiar with the idea of a triglyceride. I'm just going to say TG because we don't have time to write the whole thing out. You know what I'm talking about. A triglyceride molecule is two things. It is a three carbon chain of carbon, 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 which is essentially what we are calling glycerol. This glycerol molecule ends up being actually a source for chaining. It is actually an oxygen molecule, but I don't particularly care that you know all of the ins and outs. But then each of these is actually bound to a long chain of other carbons. So this fatty acid actually has another oxygen, but in effect, a carbon chain then starts erupting out of this. And when I stop drawing all the carbons and just draw the kinks, you can see how this starts to be the more transparent standard molecule of triglyceride. Right? Just getting sloppier and sloppier as I go. Right? These are our fatty acids. Well, how do I break these down? Well, it matters because remember the bouncing ball that we're following along with throughout this whole thing, and the same thing for glycolysis, but the bouncing ball for everything is the carbons. If you follow the carbons, you will understand things much, much better. So what are we talking about with glycerol? We're talking about a 3-carbon chain. What are we talking about with fatty acids? Well, there's actually a lot of variety in this. You're going to have some that are relatively small and short fatty acids that are like 12 carbons, and they can actually go all the way up to about 22 carbons in humans. So a lot more variation there. So mostly a pretty standard carbon is going to be 18 fatty acids. When that happens, that means essentially there's 18 carbons all in a row like this. So what are we talking about here is I want to zoom in and talk about what's happening particularly in lipolysis after I've cleaved off this molecule of glycerol. This molecule of glycerol, we already know the thing that this glycerol is going to turn into, and if you just follow the bouncing ball, there's really only so many 3-carbon things that it could potentially turn into, and so we have a 3-carbon chain. And this is a 3-carbon chain that when we release a little bit of energy, when we break these fatty acids off of it, we actually make a little bit of energy. So it's actually a nice little boon to our system. And so there's a little bit of a phosphate molecule that will stick onto this thing. Hey, what's this thing that is a 3-carbon chain with a phosphate on the third one? Well, you already know. It's a glyceraldehyde 3-phosphate. So this is actually the immediate breakdown product of breaking off these fatty acids is one single molecule of G3P. What is this G3P going to do, right? Notably, there's no energy being produced here. There's no energy in this system because we're just cleaving the fatty acids away. So we make a molecule of G3P though. These fatty acids will go off to do things that we'll eventually get to. But G3P, well, we know what that's going to do. It's essentially going to run through the second half, right? If we're just viewing this as kind of a black box of glycolysis, right? It's going to run through the second half of glycolysis, turning that molecule of G3P into a molecule of pyruvate, turning that molecule of pyruvate into a molecule of acetyl-CoA, and then that acetyl-CoA, kicking the Krebs cycle around 1 total time. So, if this were to take place, of all of these ATP that are being generated, ATP that are being made from the Krebs cycle, as well as ATP that are being generated by this second half of glycolysis. So if I stick a molecule of G3P in here, how much energy am I collecting? What is our value of energy of a single G3P? How much ATP is synthesized? Notably, I'll say directly, so that we don't have to think about oxidative phosphorylation. So pause this, or whatever you want to do here, right? Everybody gets credit for this, obviously. So, okay, now you thought about it for a second, and the answer is going to be from the second half of Krebs cycle, second half of glycolysis. Remember, you make a total of 2 ATP when you run a single molecule through. So you make 2 ATP out of that system, and from the Krebs cycle, you'll make an additional 1 AP directly. So we end up overall making a sum total of 3 ATP by taking a glyceraldehyde 3-phosphate through this system. So, why do we ignore oxidative phosphorylation? Because it's too hard to keep track of all the NADs and FADs and how much they make. And it's going to be pretty dependent on what that person and her body conditions are. Okay, so this is what's going on with our glycerol molecule. Relatively straightforward. We're just turning into something that we're already familiar with. We don't really have to learn anything new. It's really just glycolysis and Krebs cycle again. What is going to happen to this fatty acid though, right? Once I've broken this fatty acid off, I can't just take that fatty acid and slap it into the Krebs cycle. I obviously have to do a lot more changes to do this. This is where the next drawing comes from that I'm going to break my paint pad with. Why is it not working? Oh, it's because that keyboard's turned off. And this is what we now do with that free fatty acid. So it's no longer an attached fatty acid, so we start to call it a free fatty acid. I always remember it, for whatever reason, I remember it as the Future Farmers of America. That's whatever, it's just a way that I remember it in my head. I think it's a funny thing and it's weird. So that's a way that it sticks in my head and I'll never be confused about anymore. So we have that free fatty acid, and that free fatty acid has now been cleaved, and notably we have a little bit of an electrical charge to it, right? So you can see here's an oxygen is not bound to everything it could potentially be bound to. Well, that's why we call this an acid, right? It has an electrical charge to it. So when we have taken this free fatty acid, and this free fatty acid has come on over from this process of lipolysis, we've cleaved this in half. Now, what we want to do is we're going to run it through a process called beta oxidation. So beta oxidation, another way to write beta is this weird B. Beta oxidation is this process by which we break down a free fatty acid and turn it into a whole ton of energy. Lots and lots and lots of energy come out of this. So step 1 of beta oxidation is we actually have to get this free fatty acid and bump it up together against an old friend of ours who is from our hanging out left over from the transitional step. It's coenzyme A, right? Remember, coenzyme A turns that pyruvate into acetyl-CoA and then starts the Krebs cycle. Then the Krebs cycle knocks CoA off, and then this CoA floats off and finds something else to do. This is one of the things that it does. This is one of the other things that it will help out with. So we then produce a molecule from this when we add a free fatty acid together with a CoA. This is where spelling actually does matter, is we produce a fatty acid that is of varying lengths, because remember they're going to have various sizes, but it's going to be a molecule called acyl-CoA, not acetyl, acyl-CoA. This is the chemists that are mean. They just decide to make things sound very, very, very similar. Acetyl-CoA is a 2-carbon chain with a coenzyme A attached to it. When now we have multiple carbons, right, way more than 2, we call it an acyl-CoA, right? And a way that we might add more clarity to this is we could say that this is like a 16 acyl-CoA, or we could say it's a 20 acyl-CoA, depending on how many carbons we're talking about. But for us, we're just going to draw it as like a cartoon generic acyl-CoA. And this is where the Krebs, or this is where beta oxidation starts. We have a long chain fatty acid, a whole bunch of fats attached to here, and then a molecule of coenzyme A. That's really what this is at this point. And we're going to run it through beta oxidation. This is a relatively high energy state. Acyl-CoA is at the top of the roller coaster. We are about to slide down the roller coaster, and in doing so, we get a little bit of energy being released. Along the way, what we end up doing is we actually power up a couple of our weird batteries. So 2 different times we power up our weird batteries. We take and produce FADH, and we produce NADH, right, from their low power versions, FAD and NAD. Notably, I'm actually not talking about the difference between FADH and FADH squared, or H2, right? Ignore that for right now. It's not important for us. Go take OChem if you really want to do it. If you really want to get into what FAD actually means. So we make a couple weird batteries. Great. Not any ATP directly, but at the end of this, we have actually, as part of beta oxidation, there's some carbons that we need to be considerate of. There's the initial first carbon and the second carbon. And another way to write these first and second carbons is this is the alpha carbon and the beta carbon. And I think you can get the idea of what's happening here is we are actually chopping off this group and cleaving between these two. And in the effect being, we end up having 2 carbons falling off, and these 2 carbons binding with our molecule of CoA. So there's an oxygen here, and then there's that CoA molecule. And this 2-carbon chain gets cleaved and falls off. Hey, we already have a name for something that's a 2-carbon chain that is attached to a molecule of coenzyme A. This is our old friend, spelled differently, acetyl coenzyme A. Acetyl coenzyme A is that 2-carbon chain. And we've broken 2 carbons off. So if this is originally, follow the bouncing ball, if this was originally, let's say, a 16-carbon as acyl-CoA, then at the end of it, we've broken 2 of those carbons off. So what is left over from this product? Well, now it's going to be another long chain of carbons, but slightly shorter, attached to a molecule of coenzyme A. And now this is going to be, instead of a 16 acyl-CoA, we'll give it a different name, and we'll have to call it a 14 acyl-CoA. This is going to be our 2 end products. Notably, I have to add in another coenzyme A along this process. I have to add in 1 every time I run it through beta oxidation. So this is always useful, right? Anytime I want to make acyl-CoA, I'm going to have to add in a molecule of coenzyme A. So now, what do I do with these products? Well, I know what to do with acetyl-CoA. That's relatively easy. But acyl-CoA, hey, it's just the same thing. This 14-carbon acyl-CoA is the same thing as the 16-carbon acyl-CoA, just slightly shorter. So I'm going to run it through beta oxidation again. I get some weird batteries. I add a coenzyme A. I end up with an acetyl-CoA. So now I would have a 12 acyl-CoA. A do it again, then I'd have a 10, then an 8, then a 6, took me longer than I should be proud of, then a 4, and then when I have a 4 acyl-CoA and I run it through beta oxidation, what I get is I get an acetyl-CoA and another acetyl-CoA, right? So at the very end of this, eventually I'm going to have no acyl-CoA left, and I'm going to make one molecule of acyl-CoA, depending on how long that molecule of acyl-CoA is. If I have a, let's say, 18, if I have an 18 carbon acyl-CoA, well, what do I get out of that? Well, I'm going to end up making 9 molecules of acetyl-CoA, right? The carbons don't get destroyed. The carbons don't get breathed off. It's just I chop 2 of them off at a time. So effectively, I am cutting this in half. However many carbon acyl-CoA, you know how many acetyl-CoA fall out after it. So that is beta oxidation. Beta oxidation being the way that we break down molecules of free fatty acids. Hey, what are we going to do with an acetyl-CoA now? Well, now an acetyl-CoA, you are already familiar with the concept. An acetyl-CoA kicks the Krebs cycle around one time. Kicking the Krebs cycle around one time shoots off a little bit of energy. Not a whole lot, but a little bit. What kinds of energy are we expecting to see out of this? We make one molecule of FADH. We make one molecule of NADH. We do that actually 3 different times, and we make another molecule of ATP. So we get some energy out of this. It's still a benefit. But what we need to do is, this actually is not the end overall net. This is nice that we get all of these extra batteries, but we actually have to sink a cost in here at the very beginning. When we are taking this low power free fatty acid and turn it to a high acyl-CoA, I have to pay and kind of go up the roller coaster, as it were. So this is the one time that I'm ever going to use this term. We go from a molecule of ATP, and we actually go down to a very, very low power version where we actually essentially lose 2 molecules of phosphate, and we go down to a molecule of AMP. We actually lose both of these. We go all the way down to a monophosphate. So we've lost 2 phosphates to pay for this cost. So it's not quite equal in between the cost that we get out and the cost that we put in. It's still pretty close to fair and pretty close to even, but we do get some of these weird batteries out of this. And because we run these a bunch of times, the one that we have to run and worry about to make sure that we recoup our energetic costs is just doing this one time. Every acetyl-CoA that we produce after the initial one is just net profit. We make lots and lots and lots from this process. This is the reason why a triglyceride is such a very, very good storage molecule. Each of these carbons, as I cleave them off in carbon-carbon bonds, each of these carbons generates one molecule of acetyl-CoA. Another one makes another acetyl-CoA. Another one makes another. We make lots of energy off of this. We make lots of product. And then that's actually where we're going to stop. I'm not going to do ketosis because I think it's actually going to be more useful to have it in person in case anybody wants to ask any questions, because ketosis is actually pretty interesting. So here's beta oxidation. Here's fat breakdown in a nutshell. I'll see everybody on Friday.